Okay, so let's do one example live. So I got this step steel shaft. So that'll be, it'll look something like this, right? D over D ratio. So D over D, big D over little d. That ratio there is 1.2, with this diameter here being 30 millimeters. And then the radius of the fillet there is equal to 3 millimeters. So that means that we've also got an R over D ratio of 0.1. Surfaces are machined, steel has particular hardness, and ultimate strength and yield strength values are given here. So we want to use it. It's got a spur gear attached to it. So it's got a constant bending moment and a steady torque, which means that essentially as it rotates, the torque is going to provide a constant amount of stress. And the bending moment, the bending stress, is going to vary at any particular spot on the shaft as the shaft rotates. And then we have some stress concentration caused by the step shaft. So this fatigue stress concentration is given by that. So essentially, they're giving us the fatigue stress concentration, which basically means that they already went to the graphs in chapter 4. They looked up what the stress concentration factor would be for those values. Let's just do that to make, see if we come up with the same values. I think we probably will. So I'm going to pull up the stress concentration charts in chapter 4 here. So we got stress concentration factors, KT. And this is a stepped shaft. So let's just do it for the bending moment portion. So we got our diagram here. We have so our our RVD ratio is the 0.1, so that's already on there, and the line, we don't have a 1.2 line for the D over D ratio, so what we can do is just basically kind of try to interpolate a little bit. So the third line from the bottom is the 1.1. The fourth line from the top, from the bottom, is the 1.5. So we're probably looking at about, we're looking at a little bit above the 1.2 line. Let's say 1.6 there. So KT of 1.6. So that's our KT, and then we need to figure out what the notch sensitivity factor would be. So that's in chapter 8. Effect of stress concentration. Yeah, here we go. So chapter 8, figure 8.25. So we're going to be using bending. I'll erase that because I had circled that previously. All right, so the notch radius was given as 3 millimeters. So I got a 3 millimeter notch radius. So that's right here. Using bending, so we need to basically just figure out which line corresponds here. So the other value that we're given, it's got a hardness of 200 a Brinell hardness number of 200. So I got a Brinell hardness number of 200. So that's the top line. So right, that means our intersection is right here. So that looks to me to be about 0.95. So we got 0.95 and 1.6. 0.95 for our for our Q value, 1.6 for our KT. So 1 plus 1.6 minus 1 times 0.95. That gives us 0.157, which, yeah, I guess slightly off. They're going a bit lower, so I guess that probably indicates to me that they used a slightly larger, slightly smaller value for the Q, I believe. Anyways, you know, it's within within the same ballpark at least. So we'll use the value they gave us, obviously. But anyways, so they gave us that. They also told us what the modified endurance limit is. So we know what our endurance limit is there. So that's our SN for the material is 239 MPa. So if we want to determine the safety factor with respect to infinite life, and the formula we're going to be using is we're going to be using SA over SN plus SM over SU is equal to 1 over our safety factor. So we'd use that, and basically we need to find these values corrected for the safety factor. So we got our safety factor, fatigue stress concentration factor. But the torsion, we got the torsion in shear instead of in an axial manner. So what we need to do is we need to basically go ahead and convert that using our nice formula here. SA we don't really need to worry about, because basically the axial, or we'd be squaring and then taking the square root of the number. So we just need to apply the stress concentration factor, and then that's it. But for our SM, we just need to, so for our SM, axial 0, our flexion is 0, our axial is 0, bending 0. So it just ends up being, the square root of that anyways. Oh yeah, that's right, because now that I think about it, when we look at our Moore's circle, essentially if we had a pure pure shear load, it would look like that. So we would have that value there, and that corresponds to a maximum principal stress of right there, same value. So brain farts, but we applied the formula, and it ended up being giving us the value that we needed. So yes, anyways, that gives us That means that our calculation is going to be, for the bending, 60 MPa times the 1.53 divided by our Sn, which is 239 MPa. MPa is obviously cancel out, plus our mean, so that's the 80 MPa, times the 1.28 for the safety factor with respect to torsion. Sorry, not safety factor, stress concentration factor. I keep on saying that. And then our ultimate strength for the material was 700. One over factor of safety. So we got that. 60 times 1.54 divided by 239 plus 80 times 1.29 divided by 100. Take the inverse of that. That gives us a safety factor. Factor of safety is equal to 1.88. So if we're looking at our Goodman graph, then that's the one that's kind of based upon that line here, our SN SU line, based upon intersecting that one first. We've also got the SY line. So basically, and since we don't know, our graph, we don't know on the graph whether or not we're like in this quadrant where we would intersect that line first, or over here where we would intersect this line first. So we need to basically do the calculation based upon the SY line as well. So formula for that is basic. It's exactly the same as the other one. We're just subbing out SN and SU, both of them with SY. So we can basically just rewrite that as SA plus SM over SY is equal to 1 over the factor of safety. So that one would be 60 MPa times 1.53 plus 80 MPa times 1.28, and then the yield strength is 550 MPa for this one. And it's equal to 1 over factor of safety. So let's see here, 60 times 1.53 plus 80 times 1.28, all divided by 5, sorry, I divided by 500, not 550, so punch those in again. Divide by 550, and then take the inverse of that. 2.83. So basically, that's verifying to us that we are in this area here, where we're hitting the SN-SU line first, instead of hitting the SY-SY line. So that is not it. This here is our factor of safety with respect to infinite life. So the other question, the other part of the question that I kind of tacked on that I like to do here is if the required number of cycles that the shaft can sustain is reduced to 50,000, 5 times 10 to the 4, what bending stress and torsional stress could the component experience while maintaining the same safety factor? And again, that's kind of assuming that the ratio between those two remains the same. So basically, that's the effect that has on our Goodman graph is if we have, our SY-SY line stays the same. We got, if this is our original SN-SU line, then basically what we do is we just chart a new SN we chart an S 5 times 10 to the 4 line. So replace the n with infinite life with a finite life one. So, and then again, that just gets charted down to SU. So basically, as long as we're still hitting this line first, then we can expect to have more. We should expect to be able to maintain more strength. If instead we end up hitting this line here first, this portion here, then we wouldn't. Then that wouldn't be the case. But we're not worried about that because we're not worried about that occurring because we know that if we hit, well, actually no, we should double check it, I suppose. But anyways, let us figure out what the S 5 times 10 to the 4 would be. So if we go back to kind of the lecture notes, let me think here. So having a lower life means that the means that we're having higher stress levels. So the stress concentration basically has less of an effect because basically it's we're basically getting to yielding more. Whereas at the really low stress levels, those are really long life levels. That's a result of stress levels that don't reach, that even with your stress concentration don't get near the yielding. So basically, we can apply this formula here, where our Kf prime, based upon the new number, is going to be n to the power of log of the Kf divided by 3 divided by the Kf. So basically, and kind of the way that works is as you increase from 1,000 to 1,000,000 cycles, the value there increases from 1 to whatever your original value for Kf was. So in this instance, our Kf is, what was that, 1.54 for bending and 1.28 for torsion. So let's do the bending one first. Kf prime, I'm going to put a b there, is equal to 5 times 10 to the 4 to the power of log 1.53 divided by 3. 1.53 divided by 3, all divided by 1.53. So let's see here. First off, the log of 1.53 divided by 3, and then 50,000 to the power of that divided by 1.53. So that gives us 1.27 as our Kf for bending at that life level. So similar idea, Kf prime for torsion. That's going to be, 10 to the power, 5 times 10 to the power of 4 to the power of log, I think it was what, 1.28. Log of 1.28, all divided by 3. and then all divided by 1.28. So log 1.28 divided by 3, 50,000 to the power of that, divided by 1.28. So that gives us 1.15 is our Kf prime for torsion, based upon the new strength level. And then yeah, basically that's the only real effect we'll have on the by decreasing our strength there, because you know our Sn here, you know, none of those values. Sorry, that our sorry, when we do our Sn calculation, we do need to take into account, we need to take into account that we're essentially going for less. So let's see here. That's a good. So essentially, same idea kind of works here when we get we're using the bending equivalent, and it's basically a linear relationship between a linear relationship on a logarithmic scale for the Sn, or the ratio of the Sn to the Su when you're when you're going when you're moving over. So basically, that would be, we'd need to figure out where our 5 Here's, let me erase that here. Come on, there we go. So basically the log of 1,000 is 3, log of 1 million is 6. So we're got 3 divisions from here to here. Log of 50,000 is 4.69. So basically, if this is 3, then 4.69 would be right about here-ish. So the drop from 0.9 down to half for the Sn would be equal to the difference between the two. The difference between the two at the ends, so the rise basically, or drop. So that's that's 0.5 minus 0.9, so minus 0.4 times the 1.69 divided by the 3. So that'll be a drop of 0.225 basically on this scale. So from here to here, we're dropping 0.225, and that's just the ratio between our SN and sorry, our SN and our SU. So 0.9 plus that gives us a value there of SN. Here, I'm going to put S 50,000 prime is equal to 0.675 SU. So the assumption here that we can make here is that none of the other values kind of in this, none of these other values changed. The CL stays the same, CG stays the same, CS stays the same, temperature stays the same, reliability stays the same. The only thing that changes is our SN prime. So for SN prime went from 0.5 to 675, then we can go ahead and take the modified endurance limit that we were given and basically multiply that by 0.675 divided by 0.5. So multiply that by 1.35. So 1.35 times 239 MPa. That gives us a new modified limit, strength limit for 50,000 cycles of 322 MPa. So we just need to use that in our formulas. Use that and use our new stress concentration factors in the strength formulas. So again, we have, and we're trying to maintain the same ratio of the maintain the same ratio between the bending and the torsion. So the ratio between the bending and the torsion, it's 1.33. The torsion is 1.33 times the bending stress. So basically, we just need to kind of recreate this formula here with the new values for the stress concentration factors and the new value for the SN. SU obviously stays the same, and then FS we still want to maintain as 1.88. So 1 over 1.88 is equal to, let's call the SAE times the bending stress stress concentration factor of the 1.27, and that is over the new stress, the new, not endurance limit, but the new SN. And then our SME here. Our SME is equal to 1.33 SAE because we're keeping that ratio the same. So let's just plug that in there. 1.33 SAE, and then times its stress concentration factor, the 1.15. All that divided by the ultimate strength, which was what, 700 MPa. And then we can solve for SAE. Okay, so this gives us equal to, so 1.227 divided by 322. That gives us 3.94 times 10 to the negative 3 SAE. That's per MPa. And this one, 1.33 times 1.15 divided by 700 MPa. That gives us 2.185 times 10 to the negative 3 per MPa SAE. So add those two things, those two ones together. One over 1.88 is equal to 6.125 times 10 to the negative 3 per MPa SAE. So SAE ends up being 1 divided by 1.88 times that. So SAE ends up being 86.8 MPa, which means, so that's our bending stress. And then our torsional stress, our SME, is 1.33 times that. (1.33 times that is 115.5 MPa. So we've got that. That would be assuming that, again, we're still hitting this line first. That having been said, essentially the portion of the line which, like, basically you got a larger angle that could hit the SY line first. When you shift the SN up. Previously we'd only trigger that condition if we hit here. Now we trigger if we hit this. So we should double check with the SY line. So that's just going to be 1 over 1.88 is equal to our 1.27 SAE plus 1.33 times SAE times its stress concentration factor. All this divided by the yield strength, which is 550 MPa. So 550 divided by 1.88. That divided by 1.27 plus 1.33 times 1.15 gives us what our SAE would be in order to in that failure criteria. For that would give us an SAE of 104.5 MPa, which means that basically this failure criteria is triggered when the stress is higher than this failure criteria. So this is the one that gets triggered first, and we're not using this one down here. So yeah, good times. Was there anything else that was asked? Yep, no, that's about it. So that's how you kind of do, if you know the stress, it's reasonably simple to kind of find your safety factors for the components. If you know, and if you, it's not too difficult to kind of adjust for a different lifespan, basically. All right, see you.